Good morning, class. This is the third pre-recorded lecture of ECE 302. I am in the airport, I think. According to my schedule, I should be in the airport. I should be back on Friday. So this is a pre-recorded lecture on lecture 4.9 on generating random numbers. I find this a very interesting topic because it is a very good application of the transformation of random variables, or you call it the function of random variables. Let me tell you what the problem is. In the previous lecture, we have learned the technique of going from a random variable to another random variable by finding their PDFs and CDFs when I tell you the underlying probability, when I tell you the underlying function, the transformation g. Okay? So I tell you f x, and then I tell you g. I say y equals to g of x. I want you to find y, fy of y. Okay? So this is given. This is given. I ask you this. So this is the previous lecture. In this lecture, I tell you this. I tell you fy. I ask you what kind of g that we need in order to give you the y. Now that's a very interesting question because if you look at the newest homework, homework number 5, there will be problems like that. You start with some known distribution, you want to convert it to a new distribution of certain kind of shape. You ask what kind of functional transform would allow you to do that. In computer engineering, another very commonly seen problem is that I want to generate random numbers according to certain distribution. Some easily find distribution, for example, Gaussian distribution. You can, of course, you have random number generators you can generate. However, there are some customized distributions that you may not be able to see those libraries. So in those cases, how to generate random numbers? So the trick here is that we always start with a uniform random variable, and then we convert it through some transformation to the new random number. Okay, so in this lecture, I'm going to talk about the principle of designing from this uniform random variable to the new random variable. To talk about this idea, let me tell you a theorem. The theorem sort of tells you the answer. Okay, the theorem sort of tells you the answer. The answer is the following. I start with a uniform random variable u. Okay, so this is your uniform random variable u. And I want to know, I want to do some transformation. There's a g. G will take a u, and then it will give you an x. And this x will have a new distribution. So this is, of course, fu of small u. This is fx. Okay, you want to find this a new random variable, x. You want to go from the uniform random variable to the new random variable x. And then the theorem tells you that this g function is fx inverse of u, where this fx is the CDF of the random variable that you want. So for example, here it will be Gaussian, then it will be the Gaussian CDF. If you know a certain shape that you want, you can derive the CDF of that shape. Then you can apply this inversion, then you will be able to get this G. Okay, so let's see why this is the case. Okay, why is this the case? So in order to show you this result, the easiest way is to just prove it. Okay, so let's just prove it. So how do we do that? So let's start with this uniform random variable u. So u is between 0 and 1. That means your PDF is 1 when u is between 0 and 1. Now, then what would be the CDF? So fu of u, which is the CDF, it will be the integration from 0 to your small u, and then there is a ft dt this ft is your dummy variable, this t is the dummy variable, and you know this is a uniform distribution. And so, of course, I put a u here to denote that this is the uniform distribution. So you're integrating from 0 to u of this ft, so this is 1 dt, so that's going to give you 1, u, so that's easy, right? So you see that the uniform PDF is 1, and then the uniform CDF is just u. Okay, so life is good here. Now, how do we know that after the transformation, okay, so the transformation is that you send this u through this g to get this x. I want to know this fx will follow the distribution I want. How do we know that? Well, we know that this is fx inverse by the theorem. We just need to verify whether the theorem is true or not. So we want to see what is the distribution of this. What is the distribution of this x? So let's do that. So let's look at the this f. Let's don't use x. Let's define this y equals to g equals to fx inverse of u, so that I do not mess up this notation x and y. Okay. Otherwise, you will see multiple x here and there. So let me define this transformation of y equals to f inverse of u. And what I want to show is that this, or fy of, let's say, y, it has to equal to fx of y. If I can show that, then I have shown that if I send in a uniform random variable u, it goes through this transformation to get to the new random variable. Let's don't call it x, let's call it y. Okay, y will have the exact same form as what I wanted, which is the CDF of x. So this is the input, this is the output I want to show. This is whether this is true or not. How do we show that? Well, fy of y is the probability that y is less than small y. And what is y? Well, your big Y is your fx inverse of your u. Okay, so this is fx inverse of u according to my definition. Then it is the probability of u less than or equals to fx of small y, because this is a inverse, so I can put the inverse onto the right-hand side. Now I can do this operation because I know that your CDF is monotonically non-decreasing function. So I can just move it to the right-hand side without changing, worrying about this equality. Now you cannot do that, as you see in the previous lecture. When you're a cosine function, you need to worry about the range. This one, you don't have to worry about the range because fx is increasing. Okay, so once you go to this, a problem is more or less solved. Okay, why? Because this is what? This is just the CDF of your uniform random variable evaluated at this limit. And we know that this is, okay, this is fu of this fx of y. Now, you don't have to worry about what is inside. As long as you have an upper limit, it will be the thing that you put into this CDF. So you have fu of something, and we know that fu of something, it will just be that something. And so we know that this is going to be that something. Okay, so just think that fu of an apple is going to give you an apple. And therefore, fu evaluated at this fx of y, it will give you fx of y. And so you found that this fy of y will equal to fx of y. And therefore, we have shown that your this statement is true. And therefore, if I give you the random variable, the uniform random variable u, I tell you this, the CDF inverse, which is your mapping G, then you will get a output random variable, which is this y. Okay, this is your y. Y will follow the same CDF as the CDF you want, which is your fx. The reason I'm using this y here, if you're confused, is that I do not want to mess up the x and then the x. If I put an x here, that will just corrupt it's overlapping with all the notations. So I define this y here. But as long as I can show that this y is equal to this x, we're all good. So this is a very, very good illustration of how do we use this transformation of random variable. We can actually use this technique to go in and then find out the transformation that we want. So what is the idea here? Well, let's say I give you the computer, Python, or MATLAB. How do we actually program it? Well, we can start with a random number. So you call random dot random uniform random variable between 0 and 1. You draw this, let's say 10,000 samples, and then you define this f inversion. Okay, fx inversion. You define y equals to the other thing. Then your distribution of y will follow the fx. And here is a simple MATLAB illustration. Suppose we are told that this fx inverse, this formula here, is given by 1 over lambda log of 1 minus u. Let's say this is given to you already. Then the step number 1 will be u equals to rand of a 10,000 by 1 array. And then you just call y equals to minus 1 over lambda times log of 1 minus u. So here the input would be an array of random numbers. The output would be an array of random numbers. However, the input distribution would be uniformly random. The output distribution would follow this fx. Now you may wonder, what is that fx? Okay, I give you the fx inverse. What is the fx? Well, you can do the inversion. So you say y equals to minus 1 over lambda of log 1 minus u. You ask, what is u? Well, so it would be lambda y minus, so then it will give you log of 1 minus u. Then you have e to the power minus lambda y. That will give you 1 minus u. So u will give you 1 minus e minus lambda y. So this is your fx of y. Okay, fx of y. Then what is the PDF? The PDF will just be d dy of this fy. That will give you lambda e minus lambda y. Oh yeah. So we have recovered the exponential random variable. So in fact, this mapping going from this uniform through this transformation will give you the exponential random variable. So here is an example. Suppose I want to generate the Gaussian random variable, okay, with mean mu and variance sigma square. So how do we do that? Well, we start with the uniform random variable between 0 and 1, and then the CDF of this distribution will be fx equals to this standard Gaussian x minus mu divided by sigma. So that is the CDF of x. Then what would be the transformation? Well, the transformation has to be fx inverse, right? So if I say y equals to this phi of x minus mu divided by sigma, then I ask what would be the x? X equals to something in terms of y. So how do we do that? So you start to do this y equals to phi of x minus mu divided by sigma. So you have this phi inverse of y equals to x minus mu divided by sigma. Then you have sigma times phi inverse of y plus mu will equal to x. So you have this formula here. That will be your inverse. And as a matter of fact, that your g in this example is that you set g equals to sigma times phi inverse of u plus mu. That will give you the Gaussian random variable. Now, what is this phi inverse? Well, in computer, this is just the inverse CDF. So you can easily call the command. In MATLAB, it will be ICDF. In Python, there's a corresponding command. You just put that in. Then you will be able to get this G. Then you dump in uniform random variable. Then you can get the Gaussian random variable. So if you have seen a few of these examples, you can see that this is my input. This is the CDF, the original CDF that I cared about. This is the X I cared about. I start with the uniform random variable. The transformation, it will just be the inverse of that. So let's say here, you're approaching to 0, then therefore, this number will go to minus infinity as you approach into 0. This one approach to plus infinity if you approach to 1. Now, note that this is always between 0 and 1 because it is the probability. Okay, so you just pay attention to that. Okay, so what is the principle here? What is the principle here? Let's go back to this diagram. You start with a uniform random variable. You want to go to the new distribution. So the way to think about it is this. There is a uniform random variable. Okay, and I want the new distribution. A current example would be that this is a uniform. Why don't we just use the CDF of x, right? So this is u. Why don't we just use fx? Why don't we want to use the inverse of x? So if you look at this diagram here, you start with the uniform. You start to map these values up. Okay, start to map these values up. So here, the dots, they are all uniformly spaced. Because this is a uniform distribution, that the dots, they're all uniformly spaced. You move this up, and then you go to here, then you can see that there will be a lot of concentration at this tail, because all these dots, they're concentrated. If you look at this thing here, it will be very, very concentrated. And then stuff in the middle, they are just sparsely concentrated. Right? So this is going to be your CDF. Your CDF, you have a lot of things. This is going to be your PDF. Your PDF will have a lot of things. You have a lot of things in the two tails, and you have a little thing in the middle. So that means if you look at the PDF, it will just be like this. Now this doesn't make sense, right? If you put in the fx here, you're going to get something like that. That doesn't make sense. Now, how about we apply the inversion? So if we do the inverse, we start with a uniform, and then all these dots, they are uniformly sampled. And now the Gaussian uniform distribution will be like this. Okay? So let's see. So here, these are draw the slide. Okay, so these points, they're uniformly spaced, and then if you go up this figure, so this is fx inverse. You go up this figure, then you can see that here you will have very, very sparse concentration. Stuff in the middle, they will all be mapped together, and then stuff on the tail, they are located here. So that means if you draw the PDF will look like this. This is your this is the distribution you want, right? And so that's why you can see that the reason we want to put an inverse is that you want to sort of undo the CDF effect. If you plug in the CDF itself, you're going to get the inverse mapping that you do not want. Okay, so what Ken is going to do in the following 20 minutes or so is that he's going to give you some ideas of this exponential distribution, which we already talked about, and then he will talk about the discrete case. And there's also a very interesting homework problem. It's a very, very practical homework problem where we will look at some real data, and then how do you design the functional transform in order to get to a new result. Okay, so please stay here, and then let's welcome Ken to talk about those examples. And I look forward to see you in person on Friday. Thank you very much.
Hello. Today we're going to be revisiting the lecture notes. We had an issue with the recording, so we're making it on the iPad. We're going to go through the slides that Dr. Chan left for us in class that we also went through in class. We're going to start with example 2. So example 2, we want to generate exponential random numbers from a uniform random number. And to do this, we use the same high-level outline that we did last time. You start off with a uniform. U is a uniform distribution, and you'd have a CDF of the ideal distribution as defined as f of x. And this is just the exponential distribution. You can look that up or derive it yourself. So in order to get this transform that we need, we're going to apply some function to u. We're going to use the inverse of the CDF on the random variable u to get this equation here, this negative 1 over lambda log 1 minus u. And you can see the relationship between f of x and g, which is again the inverse of f of x. And you can maybe visually even see how the composition of these two functions would be the identity. On to example 3. Example 3 is our first function where the inverse is not going to be well defined, might be something more to think about. So we want to generate from, again, a uniform random number, 4 different integer values, 1, 2, 3, and 4, according to this histogram here. So 0.1, 0.5, 0.3, 0.1. From this problem statement up above, this section up here, you should be able to come up with this f of x down below. But we've written it out here on the slide for you, but on an exam, you should be expected to come up with that quantity yourself. So again, the setup's the same. We have u as a uniform and the CDF of a target distribution. And we can write out the f of x explicitly as a piecewise function. If we plot f of x like we did down here on plot A, and again, there's going to be this g of u that we're going to find on the next slide, and that's given in the right-hand side of this plot. Notably, you can even label this section 1, this section 2, this section 3, and this section 4. That gives you an idea of what the inverse CDF should be. So you can map this section on the left over to the plot on the right. So you've got this axis over here. All you have to do is map it over to this axis over here. And you can see that they look very similar. You do have to change the y values, but the x values for subplot B are given by the y values in subplot A. So piecewise functions are easy to do. They're good exam questions and homework questions. And you should be able to get the CDF just from the description of the problem. So looking at this problem again in detail, we wanted to find this g of u. And in order to find that g of u, we ended up using the intervals of the original plot. So here we've got this 0.0 to 0.1, 0.1 to 0.6, and so on for 0.3 and 0.1. Okay, in class, we noted that this right-hand equality should be removed. And that's because you want your CDF to be right continuous. Okay. We move to the summary of this set of slides. We want to generate random numbers from any arbitrary distribution f of x. In order to do that, we have step 1, which is generate a random number. So this u is going to be from some uniform. And we start with a uniform because this is the simplest to think about in terms of our inverse CDF method. And then step 2 of this inverse CDF method is we're going to take y and we're going to set that equal to the inverse CDF of your target distribution. So this is, again, the target f of x is the goal. And so you end up with the y having the CDF that you'd want. In class, we also went over a practice problem, which we will do here too. We started it. So we're going to start the practice problem here. This is homework 5, problem 1. So here is homework 5, exercise 1. We went through the beginning of A. And so the goal is you've got this y is equal to sine. And you want to find the PDF of y. So you know that f of y is the derivative of the CDF. Okay, so we're going to start with the CDF. So we know that and now we know that x, the other important fact is that x is uniform -2 to 2. Because x is uniform -2 to 2, we can actually plot the range of y. So we have this plot here. And we're going to use the plot of sine. And so if x ranges from -2 to 2, that means that y is going to be contained in this interval here. This section of the plot here is 1 to 1. That's awesome. That means because of this picture, we can do this. This step here, this is the ECE 302 step. This is one of the most important parts of the problem. And this is the part that's super tricky. It worked out nicely on this homework example. You should think that in general, it will not work out nicely. You could have a parabola. That means that for every y value, you've got 2 x values. You could have had the interval include many bumps if the range of x were larger. In general, it does not work out so nicely, and you should think about that carefully. In class, we ended up starting the derivative, and that's where we finished. So we're going to do that here. And we actually know, right, this is the CDF of a uniform distribution. So that's known. No problem. And then that's going to be equal to this. So we didn't finish this in class, so I'll stop here. But you'll end up with some expression. The final part we will note is that you need to specify the range of y, or the domain. This is the other ECE 302 component. This is just, your old calc class. We don't really care if you know that. We really care if you specify the domain of fy of y. That's part of this course. So what can it be? What are the legal values and how would you find that? Okay, thank you. Have a good day.